Section 6.4 is on exponential growth and decay. Our essential question is, what are some of the characteristics of exponential growth and exponential decay functions? Learning targets we're not going to talk about because you guys should already discuss those in your small groups to decide on your learning resources. We're going to start this lesson off by looking at an example of something you guys probably already know a lot about, mitosis, meiosis, cellular division. Specifically, in each of those situations, we start off with one cell. That one cell splits into two cells. Those two cells split off into 4 cells. Those 4 cells split off into 8 cells, and so on and so forth. Which we can really use an exponential model to represent. Y is equal to 1 times 2 raised to x. 1 is that starting value. 2 is the number we're constantly multiplying by. And really what we're going to be doing today is we're going to be learning that this 2 really can be rewritten as 1 plus 1, which really represents, the first one represents staying the same. This plus 1 actually represents what percent growth we're having, or what percent decay we're having. Specifically, this is 100% growth. That's kind of what we're going to be looking at this lesson. So, to kind of hop right into this, we're going to look at the basic form for exponential growth and exponential decay functions. An exponential growth function occurs when a quantity increases by the same factor over equal intervals of time. So we've kind of already looked at a lot of exponential functions. This is just when our base is bigger than 1. Our exponential growth functions are a function in the form y equals a times 1 plus r raised to the t power. The reason why we're rewriting the base as 1 plus r, which in the past we just said b, is because this allows us to determine what r is. And r is really representing the rate of growth, what percent we're growing by, or you could write it as a decimal as well. So in this situation, we know that a has to be greater than 0 because we have to have some sort of starting value. And because this is growth, that means my r value is positive. So again, this is something you already know. Y, your final amount, is equal to a, your starting value, your initial amount, your y-intercept, times your growth factor, which is really just our base in previous lessons, okay, which is really 1 plus a rate of growth raised to the t power representing some time. Exponential decay is the same exact thing, except right now instead of adding on that rate, we are subtracting away that rate. So our base is going to be smaller, we're going to be decaying, we're going to be getting smaller as we go to the right of this function. So, pretty straightforward from what we already know, but that's kind of the general idea that we want to be able to get in the habit of recognizing that an exponential function can be rewritten as growth or decay to determine what percent growth or what percent decay we're looking at. So the very first thing we're going to do here is we're going to take a couple of real-life situations that are either growth or decay, and we're going to write a basic model for it. It says the inaugural attendance for an annual music festival is 150,000. The attendance Y increases by 8% each year. A says to write an exponential growth function that represents the attendance after t years. So, y, my function, is equal to, again, I always start with my starting value, 150,000. And I'm going to write this above so we can kind of see exactly what we're modeling after. Okay. 150,000 is my A value, times 1. In this situation, I'm increasing 8%. So I'm going to add on the decimal version of 8%, which is 0.08, raised to the t power. So again, pretty basic to get these models. So I know that y is equal to 150,000 times 1.08 raised to the t power. B says, how many people attend the festival in the 5th year? Round your answer to the nearest 1,000. Well now, if I'm talking about the 5th year, it simply means that my t value is 5, which means all I have to do is plug t equals 5 into my equation to figure out what the value of this attendance is. Y equals 150,000 times 1.08 raised to the 5th power. Now that I have my function with the 5 plugged in, I need to reach for my calculator because I'm not sure what 1.08 to the 5th power is. I would not be expecting to be able to do that in your head. So I'm going to take 150,000 times 1.08 raised to the 5th power in my calculator. The direction says to out the nearest 1,000. Here's my thousands place. But if I were looking at the zeros and the thousand spot, which means if I look at 3, it tells me that I'm not going to round it up, so I have 220,000 approximately. So I have approximately 220,000 people in attendance. Okay. If I were to graph this, because that base is bigger than 1, I know that if I were to just leave this in terms of t, instead of plugging in 5, this exponential growth function, which would rise as it goes to the right, it would look something like this, obviously being stretched quite a bit with 100,000 in front. So, I want you to quickly do another question that's almost identical to this. Question 1 says, website has 500,000 members in 2010. The number Y, members, increases by 15% each year. Write an exponential growth function that represents the website's membership T years after 2010. B says, how many members will there be in 2016? Round your answer to the nearest 10,000. So almost identical to what we just got done doing. I would like you to pause the video right now and go ahead and give this a try. All right, here's what I got for 1. I got Y is equal to 500,000 times 1.15 raised to the T power. The question was asking about in the year 2016, which is actually 6 years after 2010, so I know my T value is 6. Plug that into my function, and I get out approximately, I'm supposed to be running the nearest 10,000, approximately 1,160,000 members. And there you have the introduction into our lesson, exponential growth and exponential decay, which is very similar to what we already know about exponential functions in general.